2014 Level 3 Physics, Electricity Question 3. And the circuit above switch B is kept open and switch A is closed. So let's just draw that on here. So closed and left open, allowing the charge to flow onto the plates of the capacitor. So it's really just the top part of the circuit, capacitive circuit, DC. Explain why the voltage of the capacitor rises to the voltage of the battery. The essence of this is that when the current stops flowing, so when the current in the circuit equals zero, Kirchhoff's voltage law for a voltage loop has to hold true, so the sum of the voltages will equal to zero. With zero current, that means there is zero voltage drop over the resistor. So it has to match the voltage of the supply equaling the voltage of the capacitor. B, when the capacitor in the circuit is fully charged, it carries a charge of Q, 8.60 times 10 to the minus 3 coulombs. Calculate the energy stored in the capacitor when it's fully charged. CV, QV, there we go. So we know the voltage is the voltages of the supply. We know that Q is given to us above there. Next part. See the graph below shows the relationship between the voltage and the time as the capacitor charges. Sketch another curve to show the effect of an increased resistance. Time constant equals RC. Increased resistance means the time constant increases. That means it takes longer to get to the same point, so your curve is going to be underneath. Still exponential though. D, explain the effect of what I've got. Switch A is open and switch B is closed. The current changes with time. So this time we're left with the capacitor running through the inductor. And there's the, quick skim up, I think the resistor was in the branch with the capacitor, there we go. Okay, so we've got the resistor in place there. Okay, explain the effect that inductors have on currents that change with time. So the inductor, according to Lenz's law, acts to oppose the change that produces it, that's the minus, and then you've got the change in magnetic flux over the change in time. Excuse me, and change of flux is equal to L times the change in current, L being the inductance of the inductor. And so the effect inductors have on the currents that change with time. The main effect is it'll reduce it. And again, same exponential curve or so forth, that any change that's being in the circuit that is causing a change in the current, the inductor will act to oppose it, as we just saw again from that Lenz's law part, and the magnitude it opposes it by is according to Faraday's law. You can ponder that a little bit more, get into in depth at your own leisure. E, discuss how energy is stored in the capacitor and inductor at the instant switch B is closed and then while the capacitor is discharging. So we've got 2 points. At the instant switch B is closed, you have no energy stored in the, let's just check to make sure I've got my right one there. At the instant switch B is closed, there's no energy stored in the inductor. And this is capacitor and inductor. In fact, we could do a little grid here, which might be easiest to look at. We've got capacitor, inductor, and then B closed, and then while the capacitor is discharging, so that's a little bit later. Okay, so as time passes, that's our time axis, time zero when it's closed to passing later. So for the capacitor, as soon as you have it closed, it's the separation of charges, positive and negative on each plate that is storing it there. Later, the energy, since it's half QV, is going to decrease as the charge and the voltage stored on there decreases, so the energy has to decrease also. That's not necessarily the best graph to use to show that, but it's going to be less. With the inductor, initially the rate of change of current is, this is energy, half Li squared is the energy formula. So the larger the current, the larger the stored energy, and as the current is decreasing over time, you have maximum current initially, so later the energy is going to drop to zero. Yeah. The how is a bit of an issue as well, but I'll talk, that one you can think about a little bit later. And I'll have to leave my hurried and not so wonderful explanation right there at the end, because my wife is here to pick me up along with my second daughter. Say hello. Mealy, say hello.
Hello.
Just say hello. Okay. Thanks. Sorry. You'll have to look at the solutions to get into more detail.